Hello, we are Group 4, and welcome to our deep dive into data-centric AI practice. Our project, Hotel Booking Cancellation Prediction, served as a case study for the CA6003 curriculum. Today, we'll demonstrate how best practice in data governance and preparation can transform raw hotelier data into actionable predictive insights. This is our team division of labor. We collaborate to complete the entire pipeline. Su Mingze was responsible for evaluation and conclusion. Hu Zihao was responsible for data cleaning. Cao Han was responsible for modeling, and Xu Jianfeng was responsible for project proposals and data acquisition. Our presentation follows the standard data science life cycle: instruction, data diagnosis and cleaning, future engineering, model training, evaluation, and conclusion. Booking cancellations are a major headache for revenue management. Our core belief here is simple: clean, well-prepared data actually beats complex algorithms. To prove this, we set up an A/B experiment. On one hand, we have our leading model, the control group, trained on raw data with manual cleanup. On the other, we have our governance model. This one is the star of the show, built through rigorous logic checks and hotel-tailored features. Our initial audit revealed a dirty reality. The heat map shows massive missing data in company and agent columns. A leading job would lose 99% of data. We also found logic errors like ghost bookings and negative room rates, violating basic business logics.
Okay, the next section is the future engineering. We found a critical behavioral bias, the planning fallacy. The zero A shows a high density of cancellation restores for long lead times. The zero B quantifies this cancellation rate surge from less than 10% for same-day booking to more than 50% for long-term ones. However, the red line shows this high-risk early birds get the lowest prices. To fix this, we implemented data governance. We removed ghost booking and negative prices. Usually, we prevented data leakage by dropping reservation status. Instead of dropping roles, we use domain imputation. The fielding is missing children with 0 and the country with the mode PLP. Okay. For future engineering, we address the skewness, where the lead time distribution was heavily right-skewed. We applied a log transformation to normalize it, improving the stability of our linear models. The final, for temporal features, we avoided one-hot encoding. Instead, we used cyclical encoding sine or cosine, as shown in the circular plot. This keeps the mathematicals the proximity between December and January, the capturing true seasonality.
Moving to our feature engineering phase, we first addressed the distribution of numerical features. As shown in Visual 3, the original lead time data was heavily right-skewed. To fix this, we applied an npdoc log1p transformation to achieve a more normal-like distribution. This normalization is a critical step because it prevents extreme values from destabilizing linear models, ensuring more reliable predictions. Next, we tackle the challenge of temporal data. Standard one-hot encoding often fails for months because it ignores the cyclical nature of time. It doesn't recognize that December and January are actually close together. Our solution was to map months to sine and cosine coordinates. This cyclical encoding preserves temporal proximity. allowing a model to capture seasonal trends accurately. Next, let's look at the results. Our baseline model initially showed 75% accuracy, which might seem acceptable, but it was actually an accuracy trap. With a recall of only 61%, the model suffered from very high false negatives. Due to class imbalance, it essentially defaulted to predicting that everyone would stay, making it useless for identifying the very cancellations we aim to prevent. In contrast, our final model achieved significantly higher performance. We reached an AUC score of 0.9. This score demonstrates strong discrimination power, meaning the model is now highly effective at distinguishing between the stay and cancel classes. This confirms that our data governance pipeline successfully extracted the necessary signals from the noise. Finally, we look at the operational viability in slide 14. The confusion matrix shows a dramatic improvement. We significantly increased recall and achieved a much more balanced classification. By drastically reducing false negatives, the model has been transformed into a robust operational tool. It now allows hotel management to confidently intervene early on predicted cancellations to recover potential revenue.
This chart verifies the value of governance, while the baseline managed a recall of 61%. Our pipeline boosted recall to 80%, while accuracy is 82%. This 19% gap in recall represents recovered revenue, risks successfully flagged for early intervention. The model identified non-refundable deposit, the red bar, as the primary risk factor. Conversely, request car parking, the blue bar, is a strongly loyalty indicator. Self-driving guests rarely cancel. Based on these insights, we recommend the first one is risk mitigation, enforced stricter policies for non-refundable segments. The second one is targeting loyalty, focus marketing on self-driving demographics. The last but not the least one is revenue recovery, leverage high recall to intervene early on predicted cancellation. In conclusion, our project validates that better data is greater than complex models. Reliable AI requires rigorous auditing, bias correction, and domain engineering. The data governance pipeline converted a failing model into a robust tool. Thank you.